Okay, hi, so welcome to this video where I'm going to speak about Ohm's Law. Okay, we're going to discuss what Ohm's Law is, and then we're going to look at how it relates to current potential difference graphs. Okay, they're graphs which confuse a lot of students, but once you understand the basis behind it, it becomes very simple. So let's dive straight in and have a look at what Ohm's Law states, all right? So this is Ohm's Law, and it states that the current through a resistor at a constant temperature is directly proportional to the potential difference across the resistor. All right, and the first thing I'm going to say is that this term here, resistor, okay, and down there as well. Now that doesn't mean the traditional component, a resistor, okay? It doesn't have to be a resistor. What it actually means is anything with a resistance, okay? So you can generally call anything that provides a resistance, you can call those a resistor, okay? Which is what this definition has done. Okay. What this actually means is when the temperature is kept constant, okay, the resistance of a component is constant. Because if you think about it, we know that, it's gone back down a little bit too far. We know that from our equation, okay, which you use loads, voltage is equal to current times by resistance, right? Now, it says that the current through a resistor at a constant temperature is directly proportional to the potential difference. And that means that the current times something equals the voltage, which it does, and that something is resistance. All right. Now, the way that you see the graphs, okay, and this is going on to your IV graphs, the way that you see those is you see current, okay, let me use a different color actually. You'll see current plotted on the y-axis, and you'll see potential difference plotted on the x-axis. Right, so what you've really done is rearrange things. So you have current is equal to potential difference, and to get current on its own, you've had to divide by voltage. Right, so this is really the equation that you're really interested in. Okay, and from that equation, we can work out the resistance based on any graph that we're given. All right, and I'll show you exactly what I mean now. So the graphs you'll see look something like this. All right, so you've got, let me just rub that out there so we've got room. So you have your current, okay, I'll just mark it over there. Current is on the y-axis and your potential difference or voltage is on your x-axis, right? And you have obviously numbers on your axis, and we get a graph, okay? We draw a line. Now the line can look different depending on which component we're talking about, right? And what I'm going to say here is we're talking about a general resistor. Okay, and if this line is a straight line, okay, which it perfectly is here, if it is a straight line all the way through, it tells us that that resistor obeys Ohm's law, because it means that the voltage and the current are completely, they are directly proportional, sorry, right? So the directly proportional part of Ohm's law on this graph can be visualized as a straight line. Okay, so this is a straight line, okay, it's a straight line, and therefore it obeys Ohm's law, okay, obeys Ohm's law, and if something obeys Ohm's law, we call it an ohmic conductor. Okay, ohmic just comes from the fact it obeys Ohm's law, and conductor because obviously it's conducting electricity. All right, so this is an ohmic conductor. Now, I'll rub that out just so I've got some room. What we can do is calculate the resistance, right? Because there's no resistance plotted on this graph, but we can calculate it from the graph. And so, if we think back to our equation, we said that current is equal to potential difference of voltage divided by resistance, right? So if I take any point on this line, I can work out what that resistance is by subbing in my values. And it always helps to take points on the line where you have exact points. So for example, here, right? Here, I mean, that was just a badly drawn cross, but you can see there, right, that it goes exactly through that point, and the voltage is 2. Okay, so I'm going to fill in the numbers into my equation. The voltage there is 2, or potential difference of 2, and if we read across to our current, the current is 0.2. Okay, 0.2. And so 0.2 is equal to voltage over resistance, and resistance is the thing we don't know. Okay, now I need to rearrange this to get resistance. Now if I times both sides by R, okay, I'll get 0.2 times R equals 2, right? Because obviously I've just moved it to the other side. And now we move the 0.2 over by dividing it, because this is times, so you do the opposite. Resistance is therefore equal to 2 divided by 0.2. Okay, and if you do that in your calculator or in your head, depends, then you get an answer of 10 ohms. Okay, so the resistance of whatever resistor this graph is displaying is 10 ohms. And that's something really handy, right? I've rearranged it here so you can see where that's come from. But if you want to work out the resistance from one of these graphs, you take this value of voltage and you divide it by this value of current, okay? Because resistance is equal to voltage over current. Okay, that's just rearranging this equation up here. Okay. Okay, so that's fairly straightforward. Now, you need to be able to recognize or even draw the shape of the graphs for different components, right? So not only a resistor, which is going to be ohmic. And so let's have a look at another graph, okay? And excuse my bad drawing. Normally you'll see this as a slightly smoother curve, but it still gives you the same point. Okay, so what this is a filament bulb. Okay, a filament bulb. And the first thing you should notice straight away is that we don't have a straight line. Okay, we have kind of a straight line here. Okay, so all the way down there, up there, that's basically a straight line. Okay, but the rest of it is not. It then changes its gradient, okay, and curves in either direction. One thing, by the way, you might be confused about these negative numbers. These negative numbers just mean that the current is flowing in the opposite direction, right? So, like, if you switch the terminals round on your cell or on a battery, then you get negative readings for the voltage. And if the current is forced to go in the opposite direction, you go from a positive to a negative. But they're the same. They're the same thing. It's still just electrons flowing, and the voltage is still just obviously the amount of energy per coulomb. All right. Anyway, so we can say that the filament bulb is not an ohmic conductor. Okay, the reason we can say that is because we know that the whole thing is not a straight line. And for an ohmic conductor, you will have a straight line. What that means is that as the voltage and the current are varied, the resistance has changed. Okay, if the resistance hadn't changed, then we'd have a straight line the whole way through. And so, we can actually show that, right? So I'll get rid of that so we've got some room. Let's take this point here. Quite hard to see because I've scribbled over it, but that's probably around about 0.5 there. Very, very close to 0.5 volts. Okay, and that gives you a current of 0.1 amps. Okay, so let's have a look. In our formulae for resistance, resistance is equal to voltage over current, right? Which is equal to 0.5 volts divided by 0.1 amps, which will give you an answer of 0.5 divided by 0.1 is 5 ohms. So the resistance at this point here is 5 ohms. Okay, now let's take another point. Well, I've drawn this cross here because that looks like it's on nice whole numbers. So we had 5 ohms. I'll leave that written there actually. Yep, maybe I'll move it over to here, like so. Okay, and now we do it again for the second point. Well, at this second point, your voltage is 2, okay, and your current is 0.2. So resistance is equal to voltage of 2 volts divided by current of 0.2 amps. Okay, and therefore the resistance is now, if you do that in your calculator or in your head, 10 ohms. And so you can see that the resistance has changed. The fact that resistance has not remained constant means that this is not an ohmic conductor. Okay? Alright, now, why is it not an ohmic conductor? Why does that resistance change? Well, if you think about a filament bulb, right, and I'm going to draw a terrible diagram. Yeah, that doesn't work. Draw another one. So let's say that this is a bulb, right? And you've got this here, which is the filament, okay? This is what's going to light up, because this burns hot, okay, and it produces light. Electrons must travel through there, right? And when they do, they're traveling through something which is heated up. Okay, that's heated up because it's burning bright to give out light. Okay, when the electrons travel through there, remember we said that an increase in temperature increases resistance, right? So as more electrons are traveling through there, so the current is increased. Yep. The bulb is getting brighter, and as the bulb gets brighter, the resistance goes up. Okay, because the metal ions in that filament are now vibrating more. They're opposing the flow of electrons, which is resistance. So it means that the resistance is increased, and so that is why you get this curve on both sides. Okay, because the resistance is then going up. The reason why it's pretty much a straight line to start with, so around about here, so this black part that I've drawn in. The reason why that's a straight line is because the bulb won't be that bright, which means there won't be much heat, and so the resistance won't be affected that much. And if the resistance isn't changing, then you have an ohmic conductor. When the resistance is changing because you have added heat, then you don't have an ohmic conductor anymore. Alright, so let's have a look at one more component, and that component is a diode. Alright, now this looks kind of different. Okay, so this is why I told you about the negative and positive previously, being to do with the forward and reverse direction. Now, if you remember, what a diode does is it allows current to only travel in one single direction. Okay, the way it actually does that is that the diode has a massive resistance in one direction. Okay, so like, if current tries to get through the diode the wrong way, then the resistance to that is huge, which means that the current just won't even exist, really. Okay, so like, let me just label the axis again: current and voltage. Okay, so the negative voltage means the current is going to be going the opposite way. Okay, but you see that the current is 0. Okay, there's this little dip here which shouldn't be there. It's just my drawing. Okay, it's basically flat. Your current is completely 0, just because no current is allowed through in the opposite direction. However, when your voltage is shifted to positive, so the direction that the diode is allowing, then as you increase the voltage, the current is encouraged to increase as the resistance of the diode decreases. Okay, and that alone should tell you that this is a non-ohmic conductor because the resistance has changed. And in an ohmic conductor, the resistance does not change at a given temperature. Okay, so it's not, or a non-ohmic conductor, our diode. Okay, and you can tell that by the shape of the graph. This here is a curve. This here clearly is a flat line, and then it changes. So the fact that you have a resistance which is not constant tells us that your resistance has changed and that it's not ohmic. Okay, obviously you could do calculations again. If I said that this point here, okay, has a voltage of 1 and a resistance is bang in the middle of 0.2 and 0.3, so 0.25, I could say that resistance at that point is equal to voltage over current. Okay, so the resistance is equal to a voltage of 1 divided by a current of 0.25. Okay, so that's 1 divided by a quarter, which gives us our resistance of 4 ohms at that particular point. Alright, perfect. Now lastly, I want to show you what the graph would look like for two types of resistor. Okay, so a light dependent resistor and a thermistor. Now, you know, let me just label these again. So current and potential difference or voltage. So you know that a light dependent resistor, okay, varies its resistance based on the amount of light. And in general, a light dependent resistor has a low resistance when you shine light on it. Okay, and so if I was to draw a graph, okay, might look something like this. Okay, and I'm not worried about the numbers here, but this is in bright light. Okay, and note I could have carried that on the other way actually as well. And then if I were to draw in dim light, okay, it might look something like, actually I'll draw it going all the way through. It might look something like this. Okay, and this here is in dim light. Okay, and why do they look different? Well, because the resistance is different. Okay, they are ohmic conductors when you keep the amount of light constant. Right, this is LDR, by the way, I forgot to write that. LDR, which is a light dependent resistor. Okay, they are ohmic resistors as long as you keep those things constant. So, in dim light, okay, the resistance remains high, which means that obviously your graph is going to be quite shallow. Okay, and when graphs get steeper, that's because the resistance has decreased, so the current is increasing. Okay, so in bright light, your resistance goes down and your current goes up, and that's why you get a steeper graph. They are straight line graphs though, because they do obey Ohm's law, as long as you keep the same amount of light on them. Okay? Alright, now last one. Try and have a think about how this graph would look with regards to a thermistor. Okay, try and pause the video now and either think about it or actually try and draw one. Don't worry about the numbers, but try and draw one. Okay, so I hope you've had a go at that. If not, then I'll run through it quickly now. So thermistor, if you remember, we said that it had the opposite relationship to everything else with regards to temperature. Okay, because we know that everything gets a higher resistance when it comes to increasing the temperature. A thermistor is opposite to that. A thermistor decreases its resistance when you increase the temperature. Okay, which means, remember we said that the temperature, the resistance is related to how steep the line is. A steeper line obviously means the current is going up quicker, which means the resistance is less. And so in high temperatures, on a thermistor, and not for anything else, in high temperatures you have a reduced resistance, which means you have a steeper line. So this is high temperature, okay? Whereas at a lower temperature, the resistance is higher, and a higher resistance means a shallower line, okay, like so, because the current is not increasing as it is being resisted, okay? So low temperature, okay, and it will look like that. Alright, so I hope that's cleared up the current versus potential difference graphs. They are basically just to show whether something is ohmic or not, and we can calculate resistance as a result of that. You could be asked to recognize what kind of component a graph might be. Okay, the telltale ones are the diode here, and you'll see a neater curve, but a filament bulb that looks like that. Okay, straight lines are ohmic conductors, right? And they could be a variety of things. So I'm going to stop there. That was quite a long video. I hope that has cleared that up. If you still do have any questions, then feel free to post them in the comment box below, or send me a direct email using the link. But as usual, please like and subscribe because it really does help me out. And I look forward to seeing you in the next one.